on that note, I think we're starting off. So why don't we go ahead and get started? Hi, everybody. How you doing? Um, as you all know by now, my name is Raul Briseño. I will be taking over from Ted for now on. He will come back at some point later when we're picking some topics of his interest, but I'll largely be the one lecturing. So why don't we do a couple of housekeeping stuff. Let me see if I can share my screen. Good. You see my presentation over here?
Yes, we do.
Good. All right. And you see my cursor, right?
Yes, as well.
Awesome. Great. Wonderful. So first things first, right? If you are new to this class, welcome. Just to catch you up, what you should do is send an email to pythonforphysics@odu.edu, and you will see an auto reply of this sort with tons of different links with information about the website, both in English and in Spanish, giving you information about the Slack chat that we have going on that is both in English and in Spanish, and reminding you that you do have to be 16 to be able to use Slack. We don't want you to break the law and get in trouble. So just keep that in mind. And if you want to join us in the live sessions and the stream that we're in right now, you can do that by following this link, and the calendar, the ODU Regis calendar will tell you what time these are being hosted, which are Tuesdays and Fridays, and at 3 p.m. in Virginia time. The recordings are posted on YouTube, so you can check out all our recordings over there. Right now, our YouTube page is a little bit of a mess because we have so many videos that are being compiled all the time, but eventually we'll make a little channel for Python for STEM for 2021. Okay, so you can see them all back to back. And then the Dropbox link where you can find our content, both in English and in Spanish, can be found here. So as always, I like to start by hearing how you all doing. Are you enjoying coding so far? If you haven't met Jazzy, this is my girl Jazzy. She loves to code at my computer as many times as possible. Hopefully she just codes, I don't know. And so she wants to know how you're doing. So why don't you tell us in the chat, how you doing today? How are things on your parts of the world? Oh, Anonymous is giving me a bit of a hard time about my desktop being messy. Okay. I like Anonymous. I like that kind of attitude. I appreciate it. I welcome it. A little bit of sass doesn't hurt anybody. But other than give me a little bit of sass about my desktop, why don't you tell me how you doing? Where are you coming from? Where are you in the world? How are things in your side of the world? Is it too hot? Is it not hot enough? Depending on where you are. So tell us about yourself. So while you do that, I see that people are a little shy to speak up today. Hopefully you will get less shy with time. Why don't I go ahead and remind you what we're going to be covering. So we're going to be talking about intro to data analysis and statistics. And we're going to talk a little bit about special relativity and particle physics, okay? This is what this set of lectures are going to be touching on, which probably will take me today and Friday. So I'm going to skip ahead. Since I covered quite a bit of this, I try to motivate the notion of data analysis, estimating errors. I talked about this last Friday, so hopefully you're convinced that trying to accumulate data is important, and trying to assess error, whether statistical or systematic, are important for us to really have a good understanding of nature. This is not just important in physics, it's important in atmospheric sciences, as well as in the study of infectious diseases like COVID. And here you're seeing real, honest to God data of Virginia as a function of time. So, you're going to be able to make this kinds of plots yourself. In particle physics, in particle nuclear physics, we do similar type of plots, we have histograms, points with, we take data with some means and standard deviations, etc. And so these kinds of things hopefully will make sense to you at the end of this set of lectures. So I'm going to skip ahead since I covered quite a bit of this already. The motivation, I suggested to you last time that you go check out a bunch of videos out there to like give you a little bit of the background on the science that motivated the last few slides. But now, so hopefully you did that, right? Everybody did that because you guys are great students, right? So you did that, wonderful. So now why don't we talk about some basic aspects of probability? And the way that I understand most math is by considering some simple examples and then trying to extrapolate from those simple examples into more complicated general principles. So let me start with a simple example. Let me ask, let me try to assess that the probability that if I pick out a random person from the class, that person would be female. How would I be able to assess that, right? Well, I can, in principle, just calculate that, right? Like I know everybody that is in the class, right? And I could ask each one of the persons, do you identify as a woman or otherwise, right? Here I don't have to make assumptions about whether a person is binary or non-binary, right? I can just ask the person, are you a woman or otherwise, right? And then I would just calculate the total people that self-identify as women divided by the total number of people, right? And this is data, right? I would be actually collecting this data, right? I would ask the person, and I'll have a little checkbox, and I was like, say woman, otherwise, right? And so I would tally up those numbers, and then I would divide the total number of women by total number of people, and that would give me the probability that if I pick out somebody from the audience, right, that person would be a woman, right? And so here, let me just delete this because this assumes a binary construction, a binary definition. And so we know better than that. And so I should have never had that. So let's delete that. Bloop, bloop, bloop. And we know that this number has to be less than or equal to 1, right? Because all the folks could identify as women, right? So that would make it that everybody in the class would be women. And so then I would be dividing the total number of women by everybody, which would be equal to 1. But otherwise, this number is always going to be less than or equal to 1, right? And so that's the probability, right? And this is how we would collect data. Let me see if I made this blunder and propagate it through, of course, because I just do copy and paste sloppily. So let's go ahead and delete that. This is Raul from the past that did this. So let's fix all that. Raul from the future, from the present knows better. And I think we're good. Yeah, wonderful. So let's go back. So that's how this is essentially collecting this types of numbers, right? Put in a little tally. That's my data, right? And so next I can ask, what is the probability that if I pick a random person from the class, that they would be a high school student, right? Well, I would exactly do the same exercise, right? I would just ask everybody, are you a high school student or otherwise, right? And then that would give me, allow me to determine, right? Exactly the number of people that are high school students, right? And then divide that by the total number. And then this will give me the total probability of picking out a random person from the crowd that would be, that they would be a high school student, right? And this again, for the same kind of logic, has to be bounded by 1, right? And so then the next question that I want to ask, right, is what is the probability that if I pick a random person in the class that they would be a female high school student? Okay, well, it's the same thing, right? I would ask everybody, if they identify as a female high school student, which would have to be a subset of both the women and the high school students, right? So this has to be less than or equal to these sets, right? So it's a subset. And so this number would then give me, by calculating that number, determining that number, dividing by the total number of people, that would tell me the probability that if I pick a random person from the audience, that they would be a female high school student, right? This has to be less than or equal to the probability that a person is a woman, right? Which I've labeled as PW. as well as less than or equal to both. It has to be bounded from above by both by the fact that but PW as well PHS, right? The probability the student is the person is a high school student. I can't defer, I can't say from this whether this number, which one of these is a lowest upper bound, because I need to have more information, but it has to be less than both of these. Okay, so simple probability, right? This is the basics of probability. And so now so this is a simple questions that we can ask about probability, right? And then you either have taken a probability class or you have some intuition about this when you're playing board games and you have a dice, or you're playing more sophisticated games, the probability that you get a card out of the deck, right? You can do a little bit of counting, right? And so you can make more or less risky decisions in your games given some amount of probability, right? And so good players in good games have these counting rules essentially in their head, and they're assessing these numbers as they go ahead, and so they can make more or less risky decisions, which after some enough time will pay off, right? So those are the basic ideas of probability, right? A less simple kind of question would be for me to ask, not what is the probability that if I pick a random person from the class that they would be a female high school student, but instead that I pick a random person on the street. That's much harder, right? I can't do essentially what I did here, or what I would propose here to calculate this. Why would that be the case? Well, what I would have to do, right, is I would have to go to the street, and here is an image of one of our buildings at ODU, which is in the corner of our main street, which is over here, right? The road is Hampton Road, so I would have to go to Hampton Road Boulevard. This is not Hampton Roads. Let's change it. It was Hampton Road Boulevard, right? I know how to spell to some extent. So I would have to go to Hampton Road Boulevard and start asking random people. I mean, it would be a little weird, right? But I would just like pick up people from the street and be like, are you a female high school student? And although it's weird, if I ask those people, right, I would then get a little tally, right? And then I would say, they're a female high school student or not, right? And so then they would look at me a little weird, but whatever. And then I would put numbers into no's and then numbers into yes, right? And then the total probability, right, that I would randomly pick somebody from the street and that person would be a female high school student would be equal to the ratio of the yeses divided by the no's plus yeses, right? But only in the limit that I sample every single person on the street, right? I need to sample everybody, right? Well, that would be the real probability, right? Because people are moving in and out all the time, right? And so you need to be able to count everybody just once, right? You don't want to double count. And it is in that limit that I can actually assess the probability of picking a random person from the street that they would be a female high school student. And this is really an exhausting task, right? This is really hard, right? If you might say like, this is a silly question that I'm asking, right? But it does prove a principle that like, if I want to not just get whether they're female high school, but perhaps that they're interested, the random high school student on the street, are they interested in STEM? Are they interested in programming? Are they interested in Python? And I want to be able to promote them this class for them to join, right? It would be basically would require me to accumulate nearly an infinite amount of data to be able to answer every question, right? So this seems highly impractical, right? And it is, right? It's super impractical. So this is just not going to work in general. We need to do something better. And this is where the fields of statistics come in. And one famous example by a statistician that illustrates the power of statistics in our everyday life and how sometimes accumulating data statistically can get us at the right answer much quicker than we would expect. that is illustrated in this story. So in 1906, a statistician was visiting a livestock fair, and in that fair there was an interesting contest. So it's quite popular. You probably have played a similar. You probably participated in a contest of the sort, and in fact, we could play this. Okay, remind me. I have an idea on how we could play this. So, Greg, I see your face. You want to remind me to bring up this discussion after I finish the story? All right, good. Okay, so we can. Okay, I have different ideas on how we can play this. Good, and we can perhaps play this by the end of today. Actually, okay. So let me finish my story. So what was happening in this fair, in this contest, is that there was an ox, right? So an ox looks like this. Here's an ox, funny looking animal. And the villagers were invited to guess the ox's weight. Okay, they told them, well, guess the weight, right? And so around 800 participants participated, all right? And they guessed the weight. Then what the statistician went ahead and did was they went and grabbed the entries, right? The individual guesses of each person. And after the event, they grabbed all the weights that everybody estimated, and then calculated the mean value obtained from this random distribution, right? Each person said, one person said it's 1,300 pounds. Another person said it was 100 pounds. One said it was 150 pounds, et cetera, et cetera. So you had like a random weight distribution, right? And then the statistician grabbed the mean value, and the mean value was within 1% of the weight of the actual measured weight of the ox. So this is a powerful example that illustrates that just by having masses, just having different people guess some weight, guess some number, right? You can at times, from their semi-random distribution, right, cancel each person's systematic deviation so that the average value is closer to the true value. Okay. And so that's a story. So that's a nice little anecdote that is very famous in when you think about statistics. And here's an example that we could do. Maybe we could do this, but we don't have enough people. So one simple way is that people guess my weight. That'll be an easy way. But we don't have enough just to test this idea, right? If we have enough statistics, right, people can guess my weight, and then we can see how far off they are from this. We could also grab like a jar of M&Ms, right? So people have played this when there's a jar of M&Ms, and you get to guess how many M&Ms are in their jar. We can also just grab any plot, right, and put a bunch of random set of numbers, and guess how many numbers are in that plot. The problem is that we don't have enough people, and eventually our numbers will be skewed. But maybe we can keep this in mind for later. All right. So,
Raul.
Yeah, Greg.
Perhaps what you could do is, since this video is like posted to YouTube and we have plenty of people in the Slack, we could post something this week and then give people until Friday to put like answers into a channel on Slack, and then we could maybe put a data table together for next week or Friday or something like that.
Sounds good. Okay, let me think about how we could do that easily. Maybe what we could do is like put a little video, like a 5-minute video with one question, and then send that and ask people to watch it. All right, think about whether you want it to be my weight or somebody else's weight, or something else, or like a jar. Does anybody have a jar of M&Ms around the house?
I personally don't, but another idea, it could be how many textbooks you have in your office.
Yeah, but it's not that many actually, because I took them all home.
Okay.
Okay. Think about it. So now let's say that instead you're asking what the height of the average American is, and we go into the street and start asking folks, right? And so here is the first example that you're going to start familiarizing yourself with histograms. We're going to play with histograms, and what you would find is that if you ask people randomly in the street 100 people, what you would get is the distribution of this sort. And here I've separated people into women and men. And so the men are in blue, the women are in orange. And what you find is that within a distribution of men, you see a kind of somewhat familiar type of bumpy like distribution with some outliers. Just for some scale, here's LeBron James. You probably had heard of him. He's 6'8". So he's a tall fellow. And the women, just for reference, you see Megan Rapinoe, who is she's like one of the, she's definitely, she may be the best soccer player, female soccer player of all time, and certainly one of the best of all time of men and women. She's 5'6" in feet and inches, so she's roughly around the medium. If you start accumulating more and more data, what you start to see is that this jaggedy pattern starts to clean up, and after 10,000, you have an even smoother distribution. And now you start seeing some very outlier cases. Here is Gwendolyn Christie, who is she's an actress in Game of Thrones, so she's very tall for women. And so you start to see that there's a really natural distribution in these cases that has somewhat of a long tail, not too long. And so let me clarify a couple of things. So let me go back. What you're seeing here is a histogram plot. If you've never seen a histogram plot, what it's telling you is just counting. It's just saying, I ask people what their height is, or I measure them, right? And I would say, LeBron James comes over, I measure him, and I would count 1. Oh, I see Connor has a jar. All right, jar of marbles. Is that it?
Yep.
All right.
That could work.
Yeah, that does work. Let's maybe save that for later, okay? But let's bring that back up. So here we have LeBron James. He's this tall, and it turns out that in a group of 100, there's nobody else. There's just one LeBron James, okay? And for this particular height, you find that there's 4 people, right? And so we just counted 1, 2, 3, 4, okay? And then in this case, there's 2 people, etc. And so this is just telling you the amount of people that have a given height in that little height distribution, right? This has a little bit of bin, right? It's binned. I can't remember exactly how it's been. I think I binned it in ones or around 1 inch or half an inch. And so that's what you're seeing here. It's just like in that around 80 and 80 and a half, there's 1 person, right? Around 75 and 75 and a half, there's 2 people, right? And that's what this is doing. That's all histograms are doing. They're just counting the number of events in a given distribution. So here the independent variable is height, the dependent variable is the number of people, right? This is what these figures mean. We're going to be using them, so you need to be comfortable with them. If you have any questions about that, this is perfect time to ask and ask me to stop. So what you're seeing is that as more and more data gets accumulated, you see the number of events are growing, right? So you see the scale here is closer to 100, right? While before the highest number was closer to 14, right? The largest bin had 14. Here, the largest bin has close to 100, right? And so you're starting to see that as I take more and more events, right? The total number grows, the distribution gets a little smoother, right? And I keep growing this number and it just keeps getting smoother and smoother. The total number keeps growing and growing, right? And this is the case for any distribution that you measure out in nature. This is just, it always happens. And it follows almost always, in many, many cases, the distribution follows this very Gaussian behavior. This is a Gaussian distribution. I gave you a little toy example for making Gaussian distributions with Python in the first week. I give you a little code for making this, and so we're going to be playing around with this as well. All right, so the first things that we would calculate from given this distribution is the average of the thing that we're trying to quantify. Okay, how many people have a given amount of X? Okay, so let's say that we've taken n data points of heights. So we've measured the height of n people. Okay, and so my data is a set of points that are x1, x2, all the way to xn, okay? The little index 1 through n is just telling me person number 1 has x1, person number 2 has x2, et cetera, all the way to person number n has xn, okay? Makes sense. So then the average height is just the sum of all the heights, right? I just sum all the heights, right? As if like I'm stacking all the people next to each other, right? So I put LeBron James and Christine, what's her name? Christine, Gwendolyn, Christine, all the people stack up onto each other, right? That's kind of a silly number, right? But then what we do is that we divide by the total number of people. And then that gives me the average height of all the people. All right. So I just sum over everybody and divide it. And so that's the simplest quantity that you can calculate is the average, sometimes called the mean. So I'll be calling it both. And so it's literally just x1 plus x2 plus all the way to xn divided by n. And so simple examples, let's say my distribution is 55 and 60. Well, what's the average? Well, it's 55 plus 60 divided by 2, because there's only two measurements. And so that would just be 57.5. I don't need a calculator for that, right? Then I do 55, imagine I have a set of 55, 68, 60, right? Then, okay, maybe I need a calculator for this one, or I just, work a little harder and I can calculate this easily, right? And so I sum of this divided by 3, that gives me 61. I didn't need a calculator. I could have done that, I think. Okay, so then that's the average. The next thing that is going to be useful is to tell me is a quantity that tells us how wide this distribution is, how broad the distribution is. And the quantity that tells us this is a standard deviation, is a deviation from the mean, okay? And this is so I'm just going to go ahead and give you the definition. So it's typically called sigma, and the standard deviation is just going to be the sum over all points away, the distance away of a given point from the mean squared, okay? If I didn't have this squared, I would just be summing zeros, right? Because I would just be summing all the points and then subtracting the mean value, and so then I would just get 0. So I need the squared, and then so I sum over all points, this distance squared, and then I'm going to divide by n minus 1. The fact that is that n has to be greater than 1 for this to be well defined, and this is telling you exactly that. Otherwise, you would have a distribution of 1, and so it doesn't make sense to talk about the standard deviation. And so these distributions that we're going to be considering, they're not always, not all distributions follow this behavior, but all the distributions we're going to be considering are Gaussian, or in other words, normal, and they follow a probability density of this sort. Okay, so there's a probability that the probability of accessing a given point in this distribution is given by this function. You don't need to know that, but it's just for completeness. And the nice thing about this distribution is that it's defined so that about 68% of the data, it lies one standard deviation away from the mean. So here's the way that you can read this distribution is that the mean is right at the center of the Gaussian distributions. And then what you can do is take steps forward in numbers of sigma. So here's 1 sigma, here's 2 sigmas, here's 3 sigmas, or you can take steps backwards, -1 sigma, -2 sigmas, -3 sigmas. And it turns out that around 68% of the data which you can show lies underneath this. It lies between 1 sigma up, plus or minus 1 sigma. Okay, so it's mostly peaked here, and that makes sense, right? The fact that it's 68 and not 70 or 71 is something that you can just show numerically or analytically, but it's a good number to remember. But the idea, right, is that most of it lies underneath this, right? And that makes sense, right? You're seeing it visually. Most of the area underneath this curve is here versus here versus here, right? And it starts to become less and less rapidly as you go further away. Okay. Other things that are important to keep in mind is that there's a standard deviation of the sample versus a standard deviation of the total population. I'm not gonna talk about their differences too much, but basically, if you had the full sample, right, sorry, the full population, right? Let me say that, like, I was asking this question about the height of the population, right? And I was able to calculate the height of all Americans or all of humanity, right? Then the distribution would be given by this number, okay? Which looks exactly the same as at this like pesky little n versus n minus 1, okay? If I had instead measured not the whole humanity, right, but like a subset of humanity, where like 100 people or like 1,000 people, right, then the distribution would be given by this n minus 1, right? And by definition, that this is always going to be bigger than this estimate is always going to be bigger than that of the total population. There's a technical point that it's not worth fuzzing over here, but it is important to bear in mind. And then another thing is that there's a difference that is important to separate between the standard deviation of the sample of your population. It's important to separate that with the error that you obtain on your mean. So the mean, if you do you calculate some average height of some people and you're trying to estimate the height from that group, the average height is going to have some error. You're going to have some estimate of that error. That error is not equal to the standard deviation of your sample, but it is equal to that if you divide it by a square root of n. Okay, that's one important thing. And you can show this, but we won't do this in this class. Okay, just wanted to make sure that people that are in the know of this keep in mind these different definitions. So we're mostly going to be focusing on this guy. All right, so one of the things that you can start doing now is testing these ideas yourself. You can make histogram plots, and you're going to make some histogram plots as we go forward by making some random distributed data, and we're going to give you some data to look at. Here, what I'm showing you is data that I randomly generated of 100 people and measuring where I picked their height to be around 65. I give it some distribution, some standard deviation of 2.5. So their height is 6.5 plus with a standard deviation of 2.5. And what you're seeing is that this is the kind of data that I generate. I get something that looks kind of Gaussian, right? It's not quite a beautiful bell curve, but it is jaggedy, kind of Gaussian, noisy Gaussian. And you're seeing that most of the data does indeed lie inside of this plus or minus the standard deviation, right? Which is what we expected. We expected around 68% of the data to lie there. I can continue to accumulate more data, right? And I go from 1,000 to 10,000. Let's fix this. The comma should be here, right? To 1,000,000, right? And I'm plotting. You see that I'm always plotting the mean value as a solid black line, and then the standard deviation by dashed lines. The height is always the same. The number of peoples is a y-axis, and you're seeing that basically, the distribution looks the same. The y-axis numbers grows, right? Because I'm accumulating more and more data, and then the curve gets smoother and smoother, right? But this picture, right, that inside of a standard deviation lies most of the data doesn't change, right? That's pretty consistent, right? And so it is always a good measure of both the mean value is telling us roughly the center of the data. You see that the data, and this is important, right? Even if if you know what standard deviations are, and you know all these concepts from statistics, coding and making your own plots gives you another layer of intuition for looking at data that you can generate and that you can play with and you can look at and get some intuition from it. And so that's what I'm trying to help you with, is build some intuition, right? The data is somewhat evenly, it's roughly evenly distributed around the mean, right? At least you can see that by eye, right? You have about the same amount of data over here as you have over here from the mean, right? And then the standard deviation is telling you where most of the data lies, right? 68%. And that picture remains unchanged regardless of the number of samples that you take, right? You're always getting the mean down right, and the standard deviation is covering around 68%. And so you can get a lot of, you basically can get the same information roughly, right, from doing a sample size of 1 million versus from 100, even though the data doesn't look quite as nice, right? All right, so why don't we do a simple little exercise to make sure that we're all on the same page. Why don't we do a calculation, all of us, of the mean and standard deviation of this distribution that I wrote up here. You have the definition of the mean and the standard deviation. So why don't you go ahead and calculate this? I'll give you a couple minutes and then we can do it all together. In the meantime, I've noticed you guys are a little shy today. So why don't you go ahead and tell me how you're doing, if we're going at the right pace, if you want me to go faster, if you want me to go slower. How are things in your side of the world? I'd like to hear your thoughts. Oh, you didn't see that. Yeah, I'll keep this up. And then while you do that, I'm going to take the liberty to remind you that the next session is one that should be really cool and you should not miss. So this is what the next session in REYES is going to be. It's going to be by Mithuna, who is she's a recent graduate from the University of Cambridge in UK, but she also does a lot of great YouTube videos on quantum mechanics and quantum information science and quantum computing. She's a really great speaker, and so she's going to come and join us in an hour and a half. And so you definitely don't want to miss out this opportunity to talk to her and hear from her. Quantum computing is a really fascinating field that is growing rapidly. And so I strongly encourage everybody to stick around for that. I think she is going to do a really great job of telling us all about what it can do for us. All right, I see some comments in the chat. Anybody, what are we hearing from the chat?
We have Anonymous mentioning that they are doing good right now, but they've just been relaxing while also doing some Python coding reading, trying to build their skills.
That's awesome. How is this class helping you out, Anonymous? Hopefully it has. All right, so what I'm going to do is calculate this on the fly with you. So I'm going to do this using arrays. And I think I covered this in just a second. Yeah, I'll do a histogram, so that's okay. So let's do it together. So what do you, I don't know what you guys prefer. If you prefer IPython, Jupyter, I prefer IPython. So what I did is grab these numbers, right? 78, 50, 69, 95, 69, 19. And then I put them into an array that I call X. And then the sum, the the average can be calculated using different tools. But let me do something first. Let me I'm gonna print out the length. Wait, is it like this? Yes. So this is a numpy. So, oh no, it's not. I just lied to you. So the length of n of x you can obtain by just using len and evaluating the array, okay? And so IPython imports a lot of numpy and matplotlib for you, so it makes some of the coding faster or simpler that way. So, okay, so the length is 6, good. That's consistent with what I would see, right? 1, 2, 3, 4, 5, 6, perfect, right? And then the x mean, which I'm gonna say is x bar, right? Is equal to the sum of x divided by the length of x. I'm gonna do something really quick, which is I'm gonna make this a float so I can divide by it without worrying about, it shouldn't matter, but I'm making this a float. And what this does is that it turned this integer n, which was 6, into a float. So it now has a 0.0, okay? I like to do that sometimes so that when I divide by an integer, sometimes you can get that your it can, depending on what your numbers are, if you have everything, if everything is an integer, it will give you back an integer. And so if you have something like 6.2, it will round it down to 6. And so I'd rather just make sure that everything is a float so I can get all the decimal figures in there without any issues, okay? And so let me now call x bar the sum over x divided by n. So that should be what I get. So you guys ready? You did it yourself, right? I assume that's around a yes. So let's see. I got x bar is equal to 6.33333333. Sounds about right. Doesn't seem crazy. All right. All right, now let's calculate the standard deviation. Let me do this in 2 steps. First, I'm going to calculate the variance, which is the sum. Well, it's not going to be the variance. It's going to be, yeah, let's calculate the, okay, let's do this. Let's just do it. Let's just do it. So I'm going to do the sum of numpy dot square x minus x bar, because I already calculated x bar, right? So I want to put x minus x bar. I want to square it. So you see I'm squaring everything inside of the parentheses. That's what this function square does. So x minus x bar, good. I'm going to sum over all, right? And then I'm going to divide by n minus 1. And then at the end, I need to take the square root of this. You saw this little trick that I did, that I was like all the way to the end, and then I went to the front. Anybody seen that before? So what you can do that by, in your keyboard, if you use Control A, takes you to the beginning of the terminal. All right, I don't think I made any mistakes here. Did I make any mistakes? I have a sum. And one thing that is really nice about IPython and a lot of text editors is that you see that if I hit this little parentheses, it's telling me where I'm closing the parentheses, right? Sometimes you lose sight of the number of parentheses that you have. And so this is telling you open parentheses, close parentheses. Open parentheses, close parentheses. Oh, it's so nice. And then you're dividing by n minus 1. And then you see, close parentheses, open parentheses. All right, so it's gonna work. It is gonna work. 26.17. Are we all in agreement? Am I in agreement with myself? is a real question. What do you guys think? Yeah, it looks like it. So here I did the calculation by hand. I sum all the numbers, 390, 380 divided by 6. I got 63. I got 63 here, 0.3, right? Which if I round it to 63, perfect. And then the standard deviation is just a sum of the term squared, right? Blah, 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 divided by n minus 1, which is 5, square root it. And I got this number, which gives me 26, which is equal to what I have if I round it down. Great. Any questions about that?
No questions, but Anonymous would like to let you know that that is also what they got. So you got to cross check.
Well, if you have no questions, we can move on from this adorable picture of Jazzy. All right, let's move on. All right, so let's look at histogram plots, okay? I've already shown you histograms, right? And I've told you roughly what they look like, right? Or what they mean. Now let's do an exercise together where you make your own histogram plots. And I'm gonna do them with you. So here's a little exercise. Let's start by just making a bunch of random numbers that are distributed from 0 to 1. So this is what this first bit does. And I'm gonna make 20 of them. So I'm gonna delete my X. So something that happens in coding, right, is that originally above, I define X as an array of this sort, right? Now I'm gonna rewrite X, right? I'm gonna say X is not any more of that, right? But instead it's equal to I'm gonna call this random function, which lies inside of the random module, which lies inside of numpy. So within random, random.random is a function that it inputs an integer, and then it gives you back a array with random numbers, each one from 0 to 1. Okay. So what should I get if I print out X, right? Previously, I had defined X to be this list of numbers, right? But because this command came later, right, I evaluated this command at line 11 rather than at line 1, right? It's going to overwrite what I had before. So now X is this random number, or list, this array of random numbers, right? If you look at these numbers, they're not exactly what I have here, right? In fact, they're not at all like it, right? I had 0.9, 0.5, 0.56, whatever, right? And here I have 0.01, 0.68, 0.4, right? But the point is that Python is giving me back random numbers, right? And so in fact, if I do this exercise again, I just overwrote what I had before, right? And then I call it again, and it gives me another list of random numbers, right? But note, if I print this, right, if I print X again, so what I'm doing every single time that I type X and I press enter, I'm printing X, right? And so if I do it again, it gives me back the same numbers, right? And so notice, when I called it here, it gave me 20 different numbers, right? Here they are. I called it again, I printed it, gave me 20 different numbers again. But now I haven't called this function again. And so every single time I call X, I'm gonna get the same 20 random numbers. Make sense? Good. This might be obvious or seem obvious, but it's very important that you have this like clean structure in your mind, right? If like the orders of operations really matter in math, and they really matter in computer science. Okay, so then what we're gonna do is just make a histogram with 5 bins, okay? And so we're going to use a function, a plotting function that it exists inside of matplotlib. Remember, so let's import matplotlib.pyplot as plt. In fact, IPython does this for me, right? I didn't have to import numpy as np. It was just it had already done this for me, IPython, okay? And so what do I want to do? I want to plot it inside of matplotlib. There's a function called hist, which grabs a list or an array, and it separates them into 5 bins, okay? And so let's do that. What happened? Oh, it's bins, not bin. Let's try it again. Boop. Look at this. Let's make sense of this. So I have, let's look at my data. Well, here's my data, right? This is the same as I had before, right? No, here it is. Okay. So no, it is the same, right? It should be the same. It's just reordered. Yeah. Let's do x.sort. Oh, x.sort. Yeah, perfect. Oh no. Okay. Doesn't matter. Okay, I'm confused a little bit. I don't know if I understand what these numbers are. They are the same numbers. It's just weird. I need to remember what it's doing, what it's printing out. Oh, it's printing out the edges. Is that what it is? Yeah. Right. It's printing out the edge here, the edge here, the edge here, edge here, etc. Yeah, good. Okay, cool. I'm with me. So the edges lie. So what it's doing is it's grabbing the smallest number and the largest number, okay? And it's creating 5 bins. Bin number 1, bin number 2, bin number 3, bin number 4, bin number 5, okay? And inside those bins, and it's just evenly distributed bins, right? So it's just grabbing the length from here to here, it's dividing it by 5, right? And what it's giving you back is the number of points that lie in the first bin, right? And the bin is defined from this edge to this edge, okay? And so what lies here? Well, you have 1, 2, 3, 4 numbers, right? This one is just above the second edge, right? And so it's counting. And what I did is I called the function sort, which grabs an array and it sorts it from smallest to biggest, okay? And so it just grabs, it's counting 1, 2, 3, 4, and it gives you back 4 in this region, right? Because you had one that was like here, another one was here, etc., but you have 4 total in this region, right? And then the next one will be 1, 2, 3, 4, 5. Yeah, good, right? There's none over here, right? Because the next one is 65, right? And you can see that that jumps this bin, the bin that is defined from this edge to this edge, gets skipped. There's nothing in here. And then you just count the numbers in this one and this one, right? And what you can count, right? What's important, right, is that we started with 20 random numbers, right? And how many numbers are being counted here, right? You got 4 in the first bin, right? So that's 4. Let's count 4. 5 on the second bin, right? Then 0, good. Then 5, then 6. It's 20, good. All right, so it's just doing accounting in a different way, right? And then I can make this as jaggedy as I want, right? I have this freedom of these bins, right? The number of bins. I could have done not, 5, but I could have done 6. And so it's going to give me it's going to look a little different, right? But it's still the same data. The data hasn't changed, right? The figure has changed because I've asked it now Now shove this data into 6 bins, right? Instead of 5. Now let's shove it into 7, into 8. Eventually, so having a hard time. I mean, it's pretty cool to look at, right? Eventually, I could do, I will have more bins than there's data, right? And so let's say I did 100. What am I going to see here? So I have more bins than data. So weird limit, but it's not impossible. Nothing wrong with that. All right, let's just check it out. Let's see what happens. Woo! I was not expecting this. Okay, I expected most of this, but I didn't expect all of this. So what I expected to see, which is most of this, is that I would get, you have like the bins are so small, right? That you basically are just counting 1, right? The bins at most allow for a single count, right? And so then you have 1 count, 1, 1, 1. And then most of it would be zeros, right? I was not expecting this. That's pretty cute. So the bins are like, still have a width, right? And there's still a probability that even if the width is tiny, that you would have two in there. All right, let's do 1,000 for fun. All right, good. You can see the separation now. Let's make this big. That's what I was waiting for. You can zoom in. You can see the separation is just really tiny, and they both lie inside this bin. Cool. So you can see this is what the data, right? These points are really what the data looks like, right? Oh, this is weird. Oh yeah, there it is. Cool. This is why I love programming. It's like you think you understand something, and then sometimes it's like it's a good way to refresh your mind. Like I thought that like with 100, right? I would just have 1 at most, but that's not how probability works. That's not how random numbers work, right? You can in principle have 2 numbers that are arbitrarily close together. Why not? Okay, cool. So that's how histogram works, and so you should play around with that yourself. Make sure that you can make these kinds of plots, and hopefully you build some intuition about them. I see we have a question. Or a comment? Anything that needs to be?
We actually have multiple questions, one relating to this and another relating to the mentorship program. So I'm going to go in order from this to the mentorship. The question regarding this is, what if we wanted to have different figures instead of plotting over each other? What would we do?
Oh, the easiest thing is you close. So you see I close the figure, right? And so you can just start it again. So I just regenerated it. I have 2 screens, so I'm like dragging stuff from one screen to another. So I close it and my screen pops up over there. You can do PLT that close, right? So that closes that from the terminal. It's the same command as in the that it would be generated in your codes. So if you did that everything by scripts or in Jupyter, and then you would just run it again and do this. You can just close it by hand if you're using an interactive format like IPython or Spider too, right? I think I mean a lot of interactive formats. You can just like physically close your viewer and then just run it again, or just close it from the terminal or from your script, whatever. There's multiple ways. You can also create a new figure on top of that, so you can have multiple figures, multiple like little screens. So there's different ways of doing this. Okay, so regarding the mentorship program, is that the next question?
Yeah, they
let
say
me guess. Let me guess.
Sorry to ask, but they want to know the results. So
yeah, okay. So I have some preliminary news. If so we'll tell you for sure next week, but I have some preliminary news. So preliminary that I'm a little cautious to say it. But Andrew Jakura and I are thinking about, so in short, he and I both got a total of 150 or 120 students that wanted to, somewhere between 120 and 150 students that wanted to work with us. And so what we're gonna do perhaps is a mini program for all those students. Instead of cutting down from there arbitrarily so that only a couple of students could work with us, we're thinking about making it possible that everybody could work with us for at least for some time. So we're trying to design that. We'll explain details next week. This is not necessarily going to be the case what all mentors choose to do. I don't know what the other mentors are going to choose to do. I'll find out next week. So if you apply to work with me, then there's a good chance that you'll still be able to work with me. Does that answer the question?
I think that'll hit the nail on the head.
All right. The nail has been hit on the head. All right. So here's some useful functions. What I was going to say. So in Python, there's a few functions in NumPy that calculate the mean. You can do it the way that I was doing by brute force, or you can just use this built-in function inside of NumPy. There's also functions that give you the standard deviation. You have to put in the number of degrees of freedom, which is just a shift in the function. So there's an arbitrary function that that calculates this for any n, okay? Because n could be 0, n could be 1, it could be whatever you want it to be in general. And so there's a built-in function that shifts this for you. You just have to specify the value of n. And then to make the histogram plots, right, that we're just doing, that's inside of Matplotlib, right? And so this is just a little nice reference of a slide for you to be able to do this on your own. All right. So are there any questions about that before we move on to your exercise that you're going to be doing? Because I've chatted for long enough. Let's assign some projects. Is there any questions? Let's see.
Been coming in so far.
Cool. All right. So what we're going to do is a fun little exercise, which is calculate pi, the fundamental constant of nature, right? Okay, there's many fundamental constants of nature, but pi is a famous one that we all know and love, and we have to use many, many times. So let's use it. So let me see. I think I'm gonna use connect my iPad. So, okay, we've all used you probably have learned already of this, like this very useful equation for describing the area of a circle, which is equal to the radius square of the circle times pi, right? This is one of the working definitions of pi. And what we're gonna do is use random numbers to calculate pi. And the way that we're going to do this is as follows. We're going to generate a set of numbers. So let me use my iPad. Are we recording? Okay, you can see this, right?
Yes, we can.
All right, cool. So what we're gonna do is generate a bunch of random numbers, X and Y, that are they can be positive and negative, and they just have to have a magnitude that is less than or equal to 1. All right, and so there could be something like this, right? So we're gonna pick numbers that are X and Y. They're gonna be random, right? And so this could be, let's say, 0.12. This could be -2, 1, 0.32, 0.45, 0.63, right? Negative, I don't know, 75, 0.90, or 0.15, negative, why not? And then this could be 0.25 or 3. Okay, whatever. You get the idea, right? So you just get a bunch of random numbers, right? And then what we'll then do is we're going to put them inside of a plane, right? So these are numbers that are inside of a plane. And we're going to calculate. So we're going to put them inside your plane. And so you have, the first number over here is going to be a number that is negative x-axis, but above, right? The second one is above both. The third one is also above both. And then the other one's going to be negative, but positive axis, etc. Right? And so you're going to have numbers like this, etc. Right? And so you have numbers like this, right? And so you have a list of numbers for both X and Y, right? And they all have to be bounded by 1, meaning they have to lie inside a square, right? Of length. This is length 2. So the magnitude has to be less than or equal to 1, both of the X and Y components, right? And so you can here show you how you can calculate this. You can use the same function that we used before, random.random nt, which gives you any number, any random numbers from 0 to 1, and it gives you nt of them. Same thing here. And then you just have to shift those numbers, which are from 0 to 1, to be from -1 to 1. Okay, and so you can do that this way. So basically what you end up doing is that basically the numbers that were from 0 to 1, right? If you multiply this by 2, right, it's gonna give you numbers that are from 0 to 2, right? And then if I subtract by 1, it's gonna give me numbers that are bounded from -1 to 1. Right.
Ro, can you put the iPad in front of the slides?
Sorry, like that. Right, so that's what I'm doing here. So I'm doing is I'm evaluating n random numbers. I'm shifting, multiplying by 2, subtracting by 1, right? Multiplying times 2 and then subtracting by 1. Okay. And so if then from this, right, I can calculate the radius of all of them. So the distance from the origin. And so that's just going to be, well, what is it going to be? It's just going to be, in this case, it's going to be 0.1 squared plus 0.12 squared, square rooted, right? Same thing. So what it's doing is just calculating this distance right here. Right? And the next thing that we're going to do is that we're going to identify them Here, I should do a better job on my square. I got a little sloppy here, so let's fix that.
While you're fixing your drawings, someone has asked if you could explain why you multiplied the coordinates by 2 and subtracted it by 1.
Yes. The reason why I did that was not because I'm shifting the coordinates, but it's because I created a list of random numbers that were from 0 to 1. And so that's good enough. So this function right here, the random, and t, right? It's giving me n numbers. So here, let's do it live. Let's look at the terminal. Right, so let's look back at this example, right? It looks, it's giving me the same type of function, okay? Let me call this, instead of x, let's call it x now, as I'm doing there, okay? And let's just do, let's just do 5 numbers, okay? This is giving me back numbers that are bounded from 0 to 1, right? But in this exercise, what I want to do is have numbers that go from -1 to 1, okay? And so what I'm saying is that what you can do is shift this. Well, yeah, I mean, you're shifting the coordinates, yeah, by 2, which then if I do this, you're going to see now that some numbers, unfortunately, none of the examples. Yeah. Look at this. So now if I multiply this by 2, right, now I have a number, at least one number that is above 1, right? Of course, right? This was bounded from 0 to 1. This is now bounded from 0 to 2. All right. Then if I shift this by -1, what it'll do is that some of the numbers that are positive are now going to be negative. And so this is now going to be bounded from -1 to 1. And in fact, let's just check this out. I can do this by, let's do this, some really large numbers. So let's do a million. So this is 1,000. This is a million. Okay. And what I'm going to show you is I'm going to calculate the maximum number of this shift. Actually, let's do this before the shift. So what is the maximum number? The maximum number is going to be very close to 1, right? What do you think is going to be the minimum number? The minimum number is going to be very close to 0. So it's 10 to the -8, right? Now, let me do that shift. Let me define x to be equal to 2 times x0 minus 1. Okay? That shift that I'm suggesting, right? And so now let's look at the max of this now new number x, right? What is it going to be? Well, it's going to be close to 1 again, right? Now let's look at the min. Well, I claim that it's going to be close to 0, and it makes to close to -1, and it makes sense, right? The minimum here was essentially 0. I multiplied 2 times 0. That gives me back 0, and I subtracted 1. Well, it's going to give me back essentially -1. So that's all I'm doing there. It's just grabbing these numbers that are distributed from 0 to 1 to be distributed from -1 to 1. Okay.
We also have a small definition-based question that's quite easy to pick off real quick. And how are you specifying that the random numbers are between 0 and 1 within your randomly generated array?
That's the way this function is defined. The function that I'm using from NumPy is defined to be bounded from 0 to 1. In fact, I could have modified it to be shifted from any numbers I want, but I decided to be lazy and instead introduce this shift by hand. There's many built-in functions and tricks for you to be able to do this without having to do this shift, but it's a good exercise for you to, knowing that this function is bounded from 0 to 1, to know how to do this is a form of a variable transformation. So all right, everybody with me? Cool. And so then what we will then do is given these numbers, right? What we got here, you can then count just the number of points that lies inside of the circle. So does it lie inside the circle or not? So we'll call the ones inside of the circle blue, the ones outside of the circle red. And so you're just counting the blues, okay? And so in this case, right, I would say, this one is in there, so that counts. This one also is in there. This was in there, or maybe not. I don't think that one might be, I'm not sure. Let's say no, yes, no, that. And so then you sum up all these numbers, all the ones that are inside of the circle, right? It gives you a bin that you tally, right? And so then you would have all the total numbers of the ones inside of the circle. That's going to be proportional to the area, right? Versus all the total blue and red. Well, it's going to be proportional to the area of the square, right? And so if I just use that insight, right? The number of blue, let's make this one red. So these are red to be consistent with my figure, right? I'm gonna have some reds over here, some red, some red, some red, red, and then lots of blue, right? Well, the total number of blue divided by the total number of blue plus total number of red, well, it's going to be, each one of them is going to be proportional to the area, right? So this is going to be equal to the area of the circle versus the area of the square, right? And we know that the area of the circle, well, it's equal to pi r squared, while the area of the square is equal to 2 times the radius, right? Because the radius, this is the radius of the circle, which is going to be a circle of 1, is this right here, the circle, right? And so I see that this is giving me pi divided by 4, because r2 squared is equal to 4. I have r squared divided by r squared. That's just equal to pi over 4. And so with this, I have that pi, I can calculate pi as just equal to 4 times nb divided by nb plus nr. So as I take the number of counts to infinity, right? This has to be equal to pi. Cool. So let's do it. Let's just calculate it. So that's your exercise. That's your project. Go ahead and calculate this. So write code that does this for you. So I have actually some code presented I have in the Dropbox folder if you want to look at it, but I encourage you to try this on your own, right? These are the steps that I would follow, right? There's some tricky things, right, that you need to, there's some non-trivial things that you have to do to translate this into this pseudocode into actual code, right? But that's a challenge of programming, and so you need to work through that yourself. But hopefully that's clear what you need to do. Here are some set of expectations of what you should be able to see, as well as like some useful pieces of my code. I introduce a condition that allows me to quickly, so some built-in functions of NumPy, you don't have to do this. It just makes it a little bit faster. But it have some functions that I'll let you look at the NumPy literature for you to be able to discern how to use them yourself. But I'm using extract, which given this condition, it determines all the points that are inside the circle. And then, yep. So then I have x min and x in and x out, and then same thing for those that are outside. And then that allows me to make a plot like this, where I put all the points that I've obtained that are inside of the circle. I made them blue squares versus those outside. I made them into red circles. And then here I'm testing out my prediction of the determination of pi as a function of the number of dots that are inside of this figure. So when I have 100, right, I get pi, somewhat okay. When I'm closer to 1,000,000, right, it starts to converge, right? So you're seeing some variations, right? Some systematic variations away from my determined value. And so reproducing a plot like this, I think, would be quite great. And so I encourage you to do that. If you want an extra challenge, once you feel comfortable making this plot on your own, an extra challenge is to then try to estimate the error made as a function of the number of points, or perhaps just a distribution as a function of the number of points. And so what you can do is plot the histogram of the largest value, consider inside into 30 bins. So I do this here. So I make a little histogram of the possible values of pi for some large number of points. And I just repeat the exercise over and over again, right? And I see what I get for pi many, many different times. And so you see that the mean of this distribution gives me back this value, and I have a distribution with a standard deviation of this kind. So that's a nice little exercise for you to try to do. And make sure that you're able to write your own mean and standard deviation functions, that you agree with what's built into NumPy. And something that takes a lot longer if you want an extra challenge is for you to calculate pi to some desired value of accuracy. Okay. And so here is essentially, what my code does, right? It makes these two plots that I already showed you. And then I make the determination of pi many number of times, and I calculate the mean, and you can see the distribution as a function of the number of points, and you're seeing that the error decreases as I get more and more samples, as expected.
We have a question.
Yeah.
Would this be considered a Monte Carlo simulation?
You want to go ahead and answer that, Connor?
Yeah, it is. Yeah, I think the reason why it's called a Monte Carlo simulation is because you're kind of, you're just relying on luck to get your answer. But over time, in this case, unlike gambling, you kind of converge on your on the desired result. And so, yeah, you're kind of taking random points and using it to approximate something.
Yeah.
Using randomness. I don't know.
Yeah, that is the simplest example of a Monte Carlo simulation, essentially, or among the simplest. But yeah. Okay, so hopefully that's clear. I'm tempted to jump into the next topic. Maybe I'll pause for any more questions before I move on. And today I'm gonna stop a little bit early, since the next talk is one that I'm moderating. So I need to make sure that I'm not late for that, and that I take a little break between this and the next talk. But I see there's a question. Anybody wanna?
Yeah, sure. We've been asked, what exactly is a variable transformation?
Oh, it just means, yeah, variable transformation is too fancy of a word. All I'm doing is just changing the coordinates, essentially. So it's just saying I started with some, basically it just means I started with some variable, x0, right? And then I changed it to a new variable x, right? And so, yeah, I don't love jargon actually, and I did that, so I'm sorry. A lot of times I find that jargon is like, it's used for people to, I don't know, pretend like, I don't know. It's not a great thing, basically. So all I'm doing is very simple. I'm grabbing some numbers that are, let's say this is 0 and this is 1, right? And so these numbers are bounded from 0 to 1, okay? And so they can lie anywhere in here, right? And so what I did is that I inflated this first by 2, right? And so what it does is that it inflates the bounds of the numbers, right? And so it goes now from 0 all the way to 2. Did I say 0 to 2 before? I meant 0 to 1. So before it goes from 0 to 2, right? And so this was, you know, these were what the variables that I called x naught originally too at the beginning, right? So numbers that lied in there. The numbers that lie in here, I was calling them x0. Okay. Then these numbers, you know, they were here, right? And then they got inflated by a factor of 2. Inflated just because the distribution is bigger now, right? Right. And then I then shifted them by -1, right? And so now the 0 is over here still. Right? But now the thing that was 0 gets shifted to a -1 because I'm subtracting by 1. And then the thing that was 2 gets shifted to 1 because I'm subtracted by 1. And so it is this distribution of variables that I called x. So it's just transforming your variables, right? Your variable was x naught, it's being transformed to x via 2 operations. One where I multiply by 2, and then I subtract it by 1. Okay. The word transformation is just kind of fancy. It's unnecessary. Any other questions out there?
Yeah, it seems as though we have a 3-in-1 question.
Okay.
Regarding, again, the bounds of the numpy.random.random.
Yep.
And so I'm just going to read it all in full, but then try and break down what I think they're asking. So they say, back to the random number array. What if I wanted to make an array of numbers between 0 and 2, which is what you just did? What would be the specific numpy function for that? And they say, basically, how do I specify the bounds? Couldn't I just use a specified range to get the same variable transformation?
Yes. Yeah, you can. Let me just look it up. Do you remember? I think it's
dot choice, if I had to remember correctly, but it's been a minute. I mean, we Google it.
Yeah, I'm just looking it up. Change boundaries. The short of it is that I think maybe uniform might be the easiest for that. Yeah. Yeah.
There's also the random underscore integers.
Yeah, but it's giving you integers, no?
Yeah, fair enough. I guess that you'd need to, for 0 and 2, you'd have to specify. That's a good point. There's not many choices there.
Yeah, I don't I don't think, unless there's some way to create a custom distribution,
Here it is.
if NumPy has something built in like that, I'm pretty sure that you just use like NumPy multiplication and that sort of thing on the whole array. I think that's kind of what RHEL's doing is standard.
Yeah, but I mean, there's also this built-in function uniform. So uniform gives you a lower bound if you put in a lower bound. So low, high, and then the size. It gives you exactly what we just talked about. So there's an even simpler way for you to do that if you're struggling to do this variable transformation.
Sorry, I didn't see that one in the docs.
Yeah, me neither.
I think this clarifies maybe the question that people have been struggling with.
Yeah, I think that should answer what I think they were getting at.
Yeah, here I'll put it on this list.
They confirmed, yes, that's good.
Cool. Here, let me just write it here. Meanwhile, you can come up with any other questions. Random numbers between or random uniform. So it's generating uniform random numbers between -1 and 1. But you can change the bounds, right? You can make it whatever you want. So you can make this, let's make this X max. And then let's make this one X min. So that people don't think it has to be 1 or -1. Cool. Any other issues?
Just, I guess, a general question asking if there's a NumPy website to find all the NumPy functions, and there is. So they have a whole website with different descriptions of lots of different libraries.
Yeah, this is what I was just looking at.
I just sent a link in the chat to NumPy's documentation.
Cool, awesome. Yeah, and these keep getting updated too. So I mean, a lot of times things that maybe don't exist one year, they might exist another year. So yeah. All right, maybe if there's no questions about this project, right? The goal is to calculate pi. Simple, fun, easy, right? Warm and fuzzy, right? It's cool because like you always get told, that pi has, it's 3.14, blah, 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 right? But like, how do you actually know that? Well, you can just calculate it, right? And in fact, you can calculate this, you can use computers, right? Which is what you're doing here, right? But in principle, you can estimate this in, like in a backyard, right? With like friends and throwing balls into a sand pit, right? Just make a sand pit that it has, that is a square with a circle inside of it, right? And you just throw rocks into that sand pit. And after a long day of measuring, right, you should be able to get pi. So there's nothing unique about using computers to do this. It's just making it much, much faster for you. All right, so let's move on. And so I was going to introduce a new topic. I think you have heard a little bit about physics. And so I'm going to tell you a little bit about physics before I introduce the new project that we're going to be considering. So perhaps by now, hopefully by now, that as far as we know, there's 4 fundamental forces in nature their gravity, right? The thing that attracts us to the Earth, that keeps us grounded and attracts us to the sun. There's electricity and magnetism, which is what is responsible for anything related to electricity, light. It's responsible for what is allowing you to see the screen right now. Then there's a strong nuclear force, which is my bread and butter. And I think you've heard quite a bit of this from Professor Rogers. And then there's a weak nuclear force. Okay, and we're going to talk a little bit about the weak nuclear force. And these three forces have been unified by a model, which is called the Standard Model of Particle Physics. And what it basically is just this beautiful array that can describe all subatomic phenomena using just 17 fundamental particles and their interactions. And it just basically describes everything that we see in nature. Okay, and it's just amazing. The strong nuclear force, of course, is the thing that keeps protons and neutrons tied inside atomic nuclei. And this is such a powerful force, right? That if you know anything about the electromagnetic force, right, what we know is that opposite charges attract to each other, right? But same charges repel each other, right? So we know this, right? Particles have the same charge, they want to repel each other, right? Inside of the atomic nucleus, right, there's only two types of particles. They're protons and neutrons. Neutrons are neutral, they have no charge, while the protons are positively charged. So that being said, the neutrons via the electromagnetic force don't interact with anything because they don't have a charge. Yet the protons have a charge and they want to repel each other. Here I'm showing you a little cartoon of what the helium nucleus looks like. Despite these being positively charged, they're shoved in this tiny, tiny little compact object, which is 100,000 times smaller than any atom. And the force that is pushing them together is the strong nuclear force. So this force is so strong that it wants to compensate, that it easily compensates for the electromagnetic force, and it shoves these particles together. And it also not only attracts protons onto themselves, but also protons and neutrons. And so this is just an astoundingly powerful force. And now what we do modern day is not just trying to study it in terms of the protons and neutrons, but in terms of the constituents of these, which are quarks and gluons. And so this is a really fascinating field. The weak nuclear force is a really, it's essential in understanding nature as well. It's responsible for, among other things, radioactive decay. And it turns out that although atomic nuclei are largely stable, some aren't. And one example of a particle that is not stable is the neutron. So which is funny. This is a really funny thing, because if you put protons and neutrons together, they get bound and they are stable in general. So we are made of things that are stable, like carbon, some helium is in there, oxygen, etc. But if you leave the neutron alone, it will decay in the order of 16 minutes. So neutrons by themselves will decay. And the way that they decay is via this reaction that I'm showing here. In fact, they will transition rapidly, or in the order of 16 minutes, to protons. But in doing so, they will be emitting some other particles. So it would be transitioning into what is called a W boson, which is itself not stable. And then that decays into an electron and an antineutrino. And a very recent calculation, which was the most precise determination of this reaction, was published by some colleagues of mine here at Jefferson Lab. And the paper got published in Nature for being able to calculate this to such high precision, this reaction. And so this is something that is still, even though this has been known for almost a century now, or perhaps a century already, it is something that is still understudied because it's such a fundamental reaction in our understanding of nature. And so what we're going to do is simulate these kinds of decays in some data analysis, and to do that, I need to tell you a little bit about kinematics, okay? And I think perhaps this is a perfect time to stop, because I'm going to tell you about concepts of kinematics, which are some of which you see in classical physics, but then I'm going to grab those and introduce them in the context of special relativity by Einstein. And then we're going to discuss how you can study these types of decays not in reality, but close enough. I'm going to give you some tools that are close enough that in principle you can at least understand how these are studied experimentally, and perhaps give you some tools that in principle, if you wanted to be participate in such an experimental analysis, you could contribute later on. Okay, so I think perhaps this is a good stopping point. Unless there's any pressing questions, what I would encourage you all to do is to take perhaps a 10-15 minute break, and then come back later on for the session with Mithuna, so you can learn a little bit about the role of quantum information in quantum computing, which I think is going to be really fascinating. So are there any questions or comments that are brief that we can maybe cover? If not, we'll be back on Friday and we'll pick up where we left off.
So far, all we have is Shari Clea Niku says, thank you very much.
Well, thank you for being here. Yeah, it's fun having, we really love being able to do this with you. So, yeah, so why don't you go ahead, take a break, and come back to the next session. I'll be moderating it. I promise it'll be fun. So, okay. So with that,